All right, well, that should work. Before I start, in the previous flash talk, I sort of mentioned of event vision. I've been dividing my attention between this and the workshop right next door. So I don't know what has been explained about event vision this morning already, or how much people know. So who is fairly new to event-based vision sensors here? Quite a few people. Okay, so I'll keep that in mind when I talk about this, because most of the talk will be about this. So I've recently started as the former chair in Neuromorphic Systems Engineering at the University of Manchester. So it was nice to be able to get in a car here, but most of my talk will be of previous work, because I really just started there in April, so there's not a lot done. Oh, there was another remark I wanted to do at the start. This is, Mohammed mentioned, I've authored 300 publications. It's mostly students and postdocs that have authored those 300 publications. I just happen to be on them. So it's unfair how we will end up taking the credit for it. So indeed, I've set up the International Centre for Neuromorphic Systems at Western Sydney University. That's still continuing, so my deputy director there has taken it over. And now I'm setting up another one here in Manchester. And we're talking with some other places in the world as well to set up multiple of these international centres to really live up to the name international. But so most of the work I will be talking about today is from the last 5 years or so, which was done in Sydney, and which would have been a much longer trip to get here. For me, neuromorphic engineering has two clear sides to it, engineering and science sides. So on the science side, which is ultimately the thing that motivates me most, is about understanding the brain, trying to figure out how the neural systems in biology work, and then can we make things that work like that. And then on the engineering side, it is, well, we have problems that we'd like to solve in the real world with engineering solutions. Can we do that smartly by taking inspiration from biology? And therefore you need to learn more about neuroscience, and you need to learn more about engineering, and they feed into each other. The research we're doing in the centre, both in Sydney and what we will be doing in Manchester, it's quite firmly on the engineering side at the moment, looking at applications of neuromorphic engineering. That is because I've been doing neuromorphic engineering pretty much since the beginning for about 35 years. And for the first 25 years, not many people paid attention to it, which was nice and quiet. But the last 10 years, this is just exploding, the number of papers and the interest and the number of people that are doing neuromorphic engineering. And that's great to see. Everybody welcome. But it's also a hype cycle, right? So there's now this massive growth, and at some point this can't keep growing, this will crash, and people will say, oh, there's too many promises that didn't work and whatever. That's what happened to neural networks in the 80s, basically. And end of the 80s, they really tanked, and nobody worked on neural networks for about 20 years, except in the background secretly. And it took till 2010 or so for neural networks to become big and prominent. I'd like to avoid that a bit for neuromorphic engineering by having some solutions out there that we can go and prove, yes, see, these things work. Not for everything that is promised, but you can do good things with it. So that's why I have such an engineering focus at the moment. When you say taking inspiration from neural systems in biology, don't just immediately think human brain as well. Think insect brains too. There's talks about, there's actually later today talk about insect brain in the one next door too. So dragonfly is about 1 million neurons. It has about a 94% success rate at catching a mosquito once it sets off to catch a mosquito. Now, if you ever tried catching a mosquito in your bedroom, it's not easy. It's like the best success rate of any predator, as far as I know. And that's a tiny brain. It lives on about 12 to 20 mosquitoes a day. It's about a grain of sugar in terms of energy. We can't build anything like that at the moment. So if we could, already, that would be great, right? One of the successes of neuromorphic engineering that I recently started re-advertising, but this is, as you can see, it's quite an old project. I did this chip for Logitech, basically. I was working at a company in Switzerland at the time, and Logitech approached them. Can you make a chip that just looks at a trackball and tells me which direction the trackball moves in? because back in the early 90s, laptops still had trackballs in them. The touchpad hadn't been invented yet. And the trackballs with the mechanical wheels in them and so on that gunked up, they didn't really work very well. And people hated them, so Logitech wanted that. We did that based on insect vision, like insect motion detectors, made the chip that looked at the ball and did motion detection on the ball, just with a random pattern on the ball, basically. So if you got some smudges on the ball, it shouldn't matter either. And that came on the market in 1994, and up until last year, you could buy trackballs on eBay or wherever, Amazon, take your supplier of choice, and buy a trackball that had that chip in it. So for 30 years, that had a neuromorphic sensor in it, and pretty much nobody knows about it. It was there, and it was a good success. So, okay, so neuromorphic vision on the right. We see this. Is there any way to? Is this live or is this? Yes, it is. So on the right is an event-based vision sensor. It just detects changes. Each pixel does that independently. So it detects where it got brighter, and we paint that yellow pixel, or darker by a certain percentage, and we paint that blue each pixel. And then, as you can see here, we put a slow exponential decay on the color to fade back to black, just so it has some duration. Because these events, they only last a microsecond at a time, so otherwise we wouldn't see them so nicely. I'll play this back once more. So you don't see buildings because they're not changing. Nothing is changing there. But you do see rain, for instance. That's why I have to turn the lights off, because we have the right contrast here. The shadows here, you see the shadows for the car appear here once they drive into the sun, but the appearance of the car itself doesn't change very much because it's looking for percentage change. So how much light in total it has, absolute values matters. Each pixel does that independently and in continuous time on the camera. To get it off the camera, then gets timestamped with a microsecond resolution. So you can slow this down, and then video gets choppy. It's shot at a low frame rate quite quickly. Whereas this, you just collect fewer, or the events for less long, still put them in a frame. So you can make as many frames per second if you want. You could go up with this timestamp of a microsecond to 1 million frames per second sort of timestamp if you wanted to. So better way to think about this is in 3D video. Standard video is just a stack of photos, right? That's all it is. And whereas the neuromorphic data is this stream of events through X, Y, and time, so through space-time. That comes with several advantages. So the sensors are very fast to respond to changes. Here it's hailing, and we're looking at the storm, and you see the lightning. Now you can slow this well down and really track the light and deal with the brightness you get from the very bright flash and the dark background of reach millions. You see some artifacts from these horizontal stripes are artifacts from the sensor being generating too many events at that point in time to easily get off the chip. But you can really start tracking the light. So it's really, in fact, you can do 1 million frames a second equivalent here, and you can just see the tendrils here growing and sort of the backlighting of this track that's happened. Really, so lightning gets quite boring. It's almost hard to imagine, right? So fast and be able to deal with these massive brightness changes. That's one advantage of these sensors. Here we're looking directly into the sun. There's a drone flying through. And you don't look directly into the sun with a standard camera, but with these they just adapt. So the pixels that are here, yeah, they're adjusted to a really bright light level, but they're still looking for percentage changes around that light level. And the pixels here, it's hard to see with this contrast here. There's a tree here. Let's take it back for a sec. There's a tree, and that's a much darker area of the field of view. Those pixels are adapted to that. So you can see the insects coming through and things like that. So with this, didn't like me going back on that one, I think. With this, you can look at a drone hanging in the sun. The sun is here, and it has an effect on what you see, obviously, but still, you can still see the drone track track the rotors, because the camera's fast enough, work out how fast each rotor is turning. This is all around 4,000 to 5,000 RPM that these rotors are. And then if you have a model of this drone, like this sort of standard quadcopter drone, then you can start predicting how it's moving if you know how its rotors are changed, because it has to change its rotor speeds to generate with different forces to move it. So you can start doing things like that when you're looking at this. Other thing where we use the brightness and the speed is here, looking at a rocket launch in Australia. There's a NASA sounding rocket launch. The sensors on that thing were to look in the ultraviolet spectrum, so you have to get out of the Earth's atmosphere to be able to see the ultraviolet very well. And you can see this camera, so it's a good Sony video camera, but it just gets totally washed out before it adapts to overexposure. It adapts finally when the thing leaves the field of view. And here you can see a lot of details all the way through as the rocket is being launched. Okay. Another advantage is that when nothing much is happening, you don't get much data. So here on the bottom, I'm just plotting how many events per second we're getting from the camera, and it's in the 50,000 events per second, mainly generated by the stars that are moving and some clouds that might be going through. And then occasionally you can just slow down time and zoom in when you see something interesting, like the shooting star that we spotted here in the video. But here too, we're waiting for this rocket to launch, and the camera is set up, and you can just let it run. And it doesn't have to collect a lot of data, because not much is changing. And then when the rocket finally goes, which is we'll see coming in a moment, you can see that in the event rate, because all of a sudden you're generating a lot more events because you have a lot more changes. And then you can decide to zoom in. Yeah, here it's coming. You know, and you slow back time to slower, so you can watch it in real time. And so another advantage is if you are somewhere where change doesn't happen constantly, or we have long periods of silence, which is what biology has too, but then occasionally you have to be quick. And that's where these sensors are good. So we've used those to build what we call astrocytes, pun intended with that name, to look at stars and satellites to track space junk. So it's they converted shipping containers with telescopes in it on lifting platforms, and a robot controlled mount, and then event-based vision sensor on the back of the telescope. And I'll show you why, what some of the advantages are. Why is that needed? Well, there's more and more stuff in space. It's I think it's Elon Musk at the moment with Starlink. It's putting up on average 100 satellites per week. 5,000 a year. Look at the numbers here. Satellite. Where are the active spacecraft here? At the moment, this is to 2023, so we're past it now. But that was 10,000. This is doubling every year, basically, the number. Well, not anymore because we're a bit higher. You can see it's a massive amount of satellites that we're adding to what is around there in space. And then there's junk, like spent rocket bodies, things that have crashed into each other and blown into multiple pieces. This is China blowing up one of their own satellites, showing that they could do that. And you can see how much junk they generated. Of course, if China can do it, the US has to be able to do it too. So they do it a couple of years later, blow up some more junk. And then there's some other, I think this is Russia, I think, and there's an Indian one in there too. The issue with the stuff in space is that we have an orbit for it, so you know where everything is moving for the satellites that we have up there in the tracks, the jump. And when we started this, I mistakenly thought it's in space. Once you know how it's moving, you know how it's going to be moving for thousands of years, right? We can predict where the planets are going to be 1,000 years ahead, but that's not true for these satellites at all. There's still some solar winds, the ones that are in low Earth orbit, They're only 400 kilometers high. They still have a little bit of atmosphere there and so on. And they have to maneuver themselves to get out of the way of other things. Like these Starlink satellites too, they do something like, don't quote me on the exact number, but it's like 600 maneuvers a year or something like that, just to stay safe. And so you need eyes on everything that is in space, basically, at least once a day, preferably more often than that, to update where it is, so that you can keep its prediction for the orbit accurate. So that next time you know where to look. Because if you're looking with a telescope, you're looking through a straw at the sky, right? You're looking at this tiny patch of sky. If you look in the wrong spot, good luck finding the satellites you're looking for with that small visual area that you have. So it's important to do that, and to do that regularly. The way it's normally done optically is like this. So you take a photo every 5 seconds, 1 second exposure time, because the satellites are faint, so you need long exposure time on your standard camera. And you do this, and then you try and find the object in it. So this is where is Wally moment for the audience. Can you spot the satellite? Yeah, there was a really bright one going through here, right? But so everything that's moving in these stripes, they're all stars. They're all moving during the exposure time, let's say. Exposure. It's tracking the satellite. That's a dead giveaway. Where would it be when you are tracking something? In the center, right? So it's right in the middle. And if I speed this up, yeah, now you see it, right? You need to do this trick of jiggling back and forth and speeding it up so you can turn this effectively into a smooth video, and then you can see it again. Okay, so that's how it's done now. And you take these long exposure times. You don't have any temporal resolution about the data you're getting. Like 1 second of tracking and the stars and so on. So anyway, so we built this with funding in first instance from Royal Australian Air Force to look at the sky and track these satellites. And this is the second one that we built. We have 3 now arriving at a site in South Australian desert. You can see it rains. It never rains in the desert, but you put a telescope there, start looking at the sky, and it will cloud over and start raining. So we also rent these things out as rainmakers. It dried up fairly quickly, luckily. It's a shipping container, so there's a whole industry moving shipping containers about. So to move this observatory from one place to another place in the country, very easy to do. You take it there, it takes about an hour to unpack it and set it up by a human. Then it needs clear sky at night, where for an hour it looks at known stars and so on to calibrate it so that it knows more accurately how it's pointing. And then it's happily done. We then have a remote interface where we can remotely, this is sped up, where we task it, say look at this, then look at that, then look at that, then look there, and then look there, and do recordings of that. So it does these recordings of the event-based data, then we get our cameras. It does automated processing of this. So we automatically extract everything that's moving in the same direction as the stars, because they're all going the same way, because they don't move relative to each other. And then anything that's moving differently, it's likely a satellite or a piece of space junk or something like that. So we track that. Because we extract the stars, we can match that to a star database. And so the pattern of the stars you match to a database that then tells you exactly where in the sky you're looking. They give you a coordinate frame, right ascension, declination. Stars have fixed positions in that, at least in the time frames that we care about. And then, so you label the objects that you're seeing with microsecond time resolution that we have, where they are generating events in this fixed coordinate. So that's what we're doing. That extraction also happens automatically. Here there was 2, and I'm doing the same trick as I did before, jiggling the footage back and forth so that you can see it a bit more. And you can see one of them, well, it's hard to see here, but one of them is blinking and the other is glinting. You get a single glint, and you see it here in the events. This is separated event streams from that object and from that object. So from this object for 30 seconds, you get these clear peaks where it's blinking at you. And from this one, you get one glint sort of around that lasts 5 seconds or so. And then here are the tracks against the star map, and the white tracks are where our prior information told us to look for these objects. So in this case, they're right on track, these objects, for where we want to look. That's not always the case. So sometimes they're off track a bit, and then the track would need updating. So all that is done automatically. We now have over 200,000 objects recorded, and so on. And let me stop it one for a sec. And so we're now commercializing that. We have a contract here in the UK now with UK Space Command to deliver these. And we've done that through a university spin-out Optera that will be delivering these things in the UK. As a thing that will actually be used, this is the first set is to try and integrate it, but ultimately the idea is to put a network of these around the world. Both for, like UK Space Command is a UK defense related one, so they want to look at their secure satellites and so on. They don't want to tell us where to look, they want to look at their own stuff. But Optera will also set up its own network of satellites for commercial operators, right, that want to keep track of their stuff and what is there. So other thing we've done is we've put the coolest thing we've done, I should say. We've got 2 payloads on the International Space Station at the moment working, both with these neuromorphic vision sensors on it. The first one went up in December 2021, and that was a really old sensor, 240 by 180 pixels, quite noisy. Was from a sensor from 2010 or 2011, quite an old sensor already. But we knew it intimately, and when you first put stuff in space, you want to know stuff that you know a lot about. The other one went up recently, just in April this year, end of April, and that has a HD sensor in it, so it's 12.8 by 720 pixels, 2 of them. It has mirrors that can steer the direction of view. It has zoomable optics and so on. These are to relative scale, basically. So it's a much bigger payload than we have as well. This one was supposed to only work for 12 months and then be disposed of, which means they throw it into the atmosphere and burn it up. You don't get your stuff back when you send it up there. They liked it so much that it operated in the same spot until they really needed that spot until July last year. So there's 2.5 years. And then they moved to the other side of the space station. So most cases, originally, this one now and this one at the start, one camera is looking down and one's looking at the horizon. Now with this one, we still have one looking at the horizon, but it's looking up out to space, which is interesting for different reasons. And we're still getting data from both of these sensors. So with the old one, as I said, it's only 240 by 180 pixels. And as the space station moves, you're basically scanning the Earth, right? Like a photocopier scanner, where it's doing the scan line, except to do it with all the pixels on the camera. In that direction, because you know how the space station is moving, you have this high temporal resolution for detecting changes. You can build up quite a high resolution picture. As long as you know how you move and you have the time resolution, you can build a super resolution pixel in that picture in that way. In this direction, because you're not scanning, you just get the resolution you have for the pixel. So here, this is about 300 meters on the ground per pixel in the cross direction of the resolution. So that gives you an idea. Here's coastline that we're seeing. This is a picture taken, I think, at the same time from a camera nearby on the ISS. And you build this pattern of changes. And here we've done the color coding in yellow and purple. Every student, every postdoc seems to want to do these pictures with different colors for on, different colors for off. I don't know why, but it's just, it makes integrating a talk harder. But anyway, so here you can see it catches the changes, things like clouds during the day, coastline, islands that it might be seeing, scanning in that direction. This is at night. Here it's over the Suez Canal here. Cairo is down here. I'll take the background away in a moment. You can see it building up this big. And at night, of course, the main change you're seeing is the lights, urban lights. So along the coastline, urban lights, and in the city, along the streets, city centers, things like that that you pick up. Also, boats in the Suez Canal. I mean, tankers, not small boats, because of the resolution that we have with that. Things like that. The camera that looks at the horizon, when we didn't look at that footage for a while because we were so intrigued by the stuff looking at the ground. When we first looked at it, it was like, oh, that doesn't look very promising. This looks like noise, really. And the longer you look, you go, oh, maybe something is creeping down here. Maybe there's something in it, and so on. Let's do that trick that we do with the jiggling and putting a bit of exponential decay so that there's a bit of persistence on these events across the frames that we generate. Remember, the camera doesn't generate frames, but I have to generate frames to make a video, right? So I have to pick frame. And then you get this, and you go, oh, actually, so there's no noise removal in here. That's why you still see all the fixed pattern noise. As I said, this was a very old, very crappy camera. It's removable, the fixed pattern noise, but we haven't bothered with it here, just to show. So you see this is features on the Earth rotating as the ISS is flying in that direction. The stars are going up because the ISS is flying in that direction. And then you go, hey, that's got to be a satellite down there. And then the longer you look, you go, oh, maybe there's another one. Then the longer you look, you find more and more. A bit slow this, huh? So stars you extract, then you start seeing multiple satellites in here. And then because we knew where we were and at what point in time, we could correlate this with the known tracks that we had, the orbits of the satellites at that time, and where the International Space Station was as well. So you get to this if you overlay it on like a 3D Earth generated picture. And you can see again, because of the orbit that the International Space Station is at, about 400 kilometers high. That's also where the Starlink satellites are. So there's one Iridium satellite here, so just left the field of view there, and the rest is all Starlink. So we're not doing any distance ranging. This is just from known positions that we indicated the distance. It's slightly misleading. And then we can also correlate the light features we see on the ground with the known cities in that. Yeah. So then, end of April, this is the installation of the Falcon Odin, our sensor. You'll see it at the moment coming up in here, I think, in the video. If the video is playing, that is. So it very helpfully stopped for a bit while we had it. And this is sped up, right? 500 times real time. You can see that moves slow with this stuff. Okay, there it is, going out and then being installed. I mean, maybe it's really boring for you, but for me, it's still really exciting to see the stuff go on the ISS. So this too, like 50 times sped up to plug this thing in, set it up, and so on. So that's where it's operating now. And so the first data that I can share that we have back from that is doing the same as we saw with the other, looking at the ground and scanning the ground as we do. It's a narrower strip now. So this is the data that we're getting. Again, this is a photo from above that was taken a year earlier. I think, and if we compare these two, so this is the data we get as we build up the image. This is a data taken a year earlier. So this was taken in 24, this is in 2025. It's this Mount Iwate in Japan. There's this extinct volcano with snow and so on. So the snow line could be different between the 2 years as well. But you can see a very good overlay between the ridges you can see in the snow and so on. And this now has a 7-meter resolution. So that means you can start seeing trucks, cars, maybe even in the direction of travel, aircraft, things like that. So that's very exciting for us. And that is work that we're still, we're very actively working on. Hopefully we'll get a lot more results from this. So with that, I'll open it for questions while I do another sort of audience thing, if you can work out what this is in the background. But feel free to ask one. Thank you. And not the question, what is that? Yes. Yes.
So, do you get, so I guess you get in the sensors mostly, photons, right? But being in the space, you get some other kind of noise source.
Yeah, we haven't seen that. So you would expect some radiation potential issues. The sensor that's been on the ISS now for over 3 years. We've looked at its performance at the start and at the end, and statistically we can't see any difference between it. So it's not damaged by the radiation. Whether we get some noise events from radiation, we haven't actively looked into that. If we do, it doesn't look like it's a lot. Radiation is not that high at 400 kilometers high yet. If you go to where the geostationary satellites are, that's 100 times further out. That's like 36,000 kilometers away. Their radiation is much higher. And you might, we're looking at sending a sensor to geostationary orbit as well. But one of the first tests for that we will need to do is stick it in a radiation chamber and see can it deal with that radiation. That's a good question.
This one class, sorry, has noticed it great environments for vessels.
For submarine environments or marine environments?
Marine environments.
Marine environments. Yes, at the moment, well, not an application as such, but research into using it for tasks. We've shown that we can do that drone tracking that Schaik showed earlier. We can do that from a ship at distance, like at 8 kilometers distance or something like that. Well, and then the ship is moving up and up, and now things are changing, the camera's moving up. So this is without a thing. But we just use the horizon, to stabilize the horizon with from the data stream, and then they.
So do you think it's sort of being as conventional use on vessels in order to help see during storms?
Yeah, also, or like it might be easier than on land because maybe have fewer options. Although in storms you start getting really big waves too, can't easily. One of the things is somebody's put this thing on autonomous vehicle. Once the camera starts moving, everything changes. Changes happen everywhere. Even buildings start generating changes, but you change the angle of view. And so then you start generating a lot of it. And instead of being a low data rate device, now it becomes a very high rate device, very higher than one way to deal with that would be to learn to ignore the events that you already predicted on your cell phone and do that on the camera itself before you set them up. That would mean developing higher, or at least do it.
And applications with stuff like microscopic imaging, so I think neural training time proteins versus imaging.
People have looked at calcium fluorescence and things like that on microscopes and so on. You can get it to work, but you can't really get great advantages where the contrast changes often are not that high for you to get good results. It's still something that people are interested in, but it's usually an environment where you have a very controlled in-field dynamic range of light levels, for instance. So you don't need a high dynamic range where you can go from looking into the sun and seeing in the shadows at the same time, or looking at needing the speed of lightning to look at this. There might be applications there in microscopy where you're doing blindness, but I don't know.
Thanks for the super interesting thought. So in the visualizations, yellow colors based on percentage shapes. Do you find that you have to tune those parameters based on the the situation, like I imagine looking to dark space compared to something that's normal, or do you,
To some extent, but like the ones on the ISS, for instance, they operate with the same set of tappings they know. So they work better if you optimize it for the particular seeing conditions, but it usually works well enough across the whole range.
and yeah, you mentioned before that if you were mounted on a robot, you get lots of global changes, lots of data. You can see in one of the videos when the drone passes in front of the sun, it obviously casts a shadow on the sun, so it's not big global response.
Yeah, you get a big response.
Is that a thing that you can somehow count for?
Yeah, you could try and recognize those as like, okay, they're from that, right?
So if I get things right, that most of the data so far, or what we didn't see was a lot more neuromorphic sensing. So everything you're generating is really cool, but it's based on this temporal effect that we see at the sensor level.
Yep.
How much of what you're showing as well is neuromorphic in terms of the algorithms that sit behind it? Because that's an emerging field, or is it more classic computer vision sitting, taking that input?
So the algorithms for extracting the data for the stars and satellite tracking are a mix of things. The standard signal processing, I would call it, in it, as well as some event-driven processing. And we would be using that for what I showed from the ISS from space as well, where we're seeing the stars and the satellites and so on. That's the same sort of algorithm, but it's not in post-processing at the moment on a computer. No special hardware in it. In the future, I'm predicting the things. I'm predicting that we will have self-driving cars, self-driving satellites in space before we have self-driving cars all around the planet. It's getting so busy there that these things need to be able to see and react. And you don't have the same set of regulations, speed limits, kids crossing the road, dogs, footballs, you know, right? And so it's much easier environment to do it in, but it's going to be necessary. And you don't have problems with weather and so on, right? Plant cover, things like that. And so then you need to be able to do that processing in space too. Then you might not, if you have a small satellite, don't have enough power to run a PC all the time. Then you might run it on some power, like computer. But back to where I started at the beginning, I think at the moment there are much more obvious applications of neuromorphic sensing than of neuromorphic computing. Neuromorphic computing, we're still trying to work out what is for. We're creating it so that we can do it. But really, I don't think anybody knows how to use it.
I guess to go back to your very first slide, it's almost like processing bit is still in the science phase.
Yeah. We're still exactly. That's a good way of thinking about it. I'm going to steal that.